Yeah.
You hit the HDMI button at the top right. Yeah, it's 9. Okay, it's not 9 o'clock yet.
Okay. Hi, everybody. I'm Ryan Wilbur. I'm a master's student here at Ohio State. Today I'm going to be presenting this paper about residual stresses in SLS and SLM printing. It was originally by Peter, and pardon my pronunciation, Marcelius and John Pierre Kruth, written in 2006. So it's a little older, but it does a good job of tying experimental results to their theoretical model. And they have a lot of good graphs that provide visuals explaining a lot of their conclusions. So hopefully that'll come across in the presentation. So we're going to be taking a look at residual stresses in these powder bed fusion processes. The material that they were really focused on was 316L stainless steel, which is a common material as we've seen in a lot of our classwork. However, they do go into a little bit about what will change if you begin to change material properties. And one of the main things they kind of throw at you immediately in the paper is that they're only worried about type 1 residual stresses, which vary over very large distances. They're not as concerned with type 2 and type 3, which are different phases of the material, so liquid to solid, and those that arise through atomic dislocations. So we're going to be ignoring those and really focus on the process applying residual stress to the parts. So residual stress in relation to your final part, you're going to get a deformation from your intended shape, which is definitely an issue if you're going for a near net shape or net shape process, and you're expecting that your part is going to meet a certain amount of tolerances when it's actually done printing. And a tensile pre-stress can actually add to the external loading stress on a part itself, which will reduce its strength and also favors crack propagation if a crack were to form if you loaded your part. They did bring up examples about how this pre-stressing can be used to actually change the material properties favorably for a part, in particular with ceramics and glass, but they really mainly wanted to focus on reducing this tensile pre-stress. So it was well known before this paper that laser processes do apply a residual stress to your part itself. In fact, these large temperature gradients were used for a process known as laser bending, which is using the laser to actually bend sheet metal to a required shape. So the mechanisms that they talk about that actually applies this pre-stress, there were two. We have the temperature gradient mechanism, which they describe using this figure here. So the way this mechanism works is that a large thermal gradient begins to develop around the laser as you have a lot of energy heating the surface, but relatively slow conduction of heat through the part. So that's going to cause a decrease in strength of the part in that area. So when you're heating, you're going to get a bend away from the laser, and then once that material begins to cool, once you remove the laser source, you're going to begin to get a bend towards the laser direction. However, the main one they wanted to focus on in their theoretical model was the cool down phase of the molten top layers. So what that ended up meaning was we're going to get the molten top layer wants to shrink due to thermal contraction. However, it's going to be inhibited by the underlying material that it's fused to that isn't molten. So a visual to help explain this. So if we have our base plate and our part that we've already built up here, we're going to add a molten top layer to this part. And as it begins to cool, it's going to want to thermally contract. However, because it's fused to that part below, it's going to be unable to do so. And this is going to induce a tensile stress in that top layer, while also applying a compressive stress to the layers below. Now this is going to be important to explain a figure a little later on. So the model that they ended up building had a few assumptions and a few definitions for their mathematical equations. First, we are concerned with the base plate height for reasons that I'll go into in a little bit. We also need to be concerned with the part height and our layer height that we're going to be adding. We're going to assume that the base plate and the part are both at room temperature, and that the upper layer induces this thermal stress due to shrinkage, and that's going to be equal to the yield stress of the material. Then we're also going to be able to say that the stress that we're concerned with is independent of the thickness or the y direction of our part. So we're going to be concerned with a 2D model that has coordinates in the z direction, which is the build direction, and the x direction, which is along the length of the part. We're going to assume that general beam theory is valid, and there's going to be no external forces on the part and base plate combination. So the model was constructed using a force balance equation and a moment balance equation. They also applied a continuity of deformation in between the base plate and the part itself. And that was done using the strain equation, AZ plus B. And it wasn't explicitly stated, but based on how they go from these equations to their final model equations, we're also going to be applying Hooke's law, or stress is equal to Young's modulus multiplied by the strain. So taking a look at what happens in between that interface, we're going to have the same deformation of the base plate and the part itself at that interface. However, those two materials have different stiffnesses. Therefore, they're going to develop different stresses. So we can define a ratio M here, which compares the stiffness of the base plate and the part itself. And doing so, applying Hooke's equation and the strain equation that we just showed, we end up getting our force and our moment equations to look in this form, where we have an integral across the base plate, an integral across the part, and then an integral across that top layer. So solving those two equations, we can get values for our A and our B parameters, which are defined here. They have this HS term, which was actually undefined in their paper, looking at how you go from those integrals to an equation. I believe it's a sum of a few of the heights. However, they never defined what this particular variable is. I didn't go through and do the stipulation, but I believe it should be a sum, either HB plus HP plus P or HB plus H. So then that's good if we are only concerned with the residual stress that builds up if we keep our part attached to our base plate for an infinite amount of time. But we're more interested in what that part's going to be after we actually remove it from our base plate. So to do so, we're going to take a look at this relaxation stress. Now this is going to be in a new coordinate frame, Z prime, which is related to the height of the part after base plate removal using a wire EDM process. So we're going to have a constant shrinkage of the part due to just due to thermal shrinkage, and it's going to be uniform across the part.
I don't know if I
Yeah.
asked this before, but everyone know what wire EDM is? So, it gives you a little fuzzy on it. So basically, it's an electrochemical way of removing material or separating, in this case, the part from the base plate without inducing stress or induced stress or relieving stress in the part. So if you were to do this experiment and you were to remove the part by, say, a bandsaw, the vibrations of the bandsaw can actually relieve stress in the part, and therefore the measurement you did afterwards would be fictitious from what actually was in the part. So it's essentially seen as a zero stress way to remove material.
And that's going to be important for the method that they actually go about to experimentally test the residual stress that's built up across the part thickness. So yeah, going back to the relaxation stress model, we're going to have a uniform shrinkage of the part and also a deformation or curvature of the part itself. We can solve those two parameters using this equation, which is just going back to the force and moment balance. And then getting into their actual model results, they began with a 50 layers with a base plate of 20 millimeters. That's going to be important because they're going to vary the base plate thickness in some of their results, and that's going to have an effect on the residual stress. Their base plate was stiffer than their actual part material that they were printing. They're going to have a layer of 50 micrometers, and the sigma yield, which is going to be important for the graphs, is 300 megapascals. So just to help orient you to the figures that we're going to be showing, if we print a material layer on this base plate, we're going to get a compressive stress in the top layer of that base plate and a tensile stress, towards the bottom of that base plate. So then taking a look at these graphs, just to help orient you, this section of the Z coordinate is going to be the part, whereas everything else is the base plate. There's actually an error, I believe, in the paper with this figure. It says height after part removal on the x-axis, but I'm fairly certain that is incorrect. It should be height before part removal. So we have our tensile stress zone that we just showed with that figure before. Here, our compressive stress zone, and this is the stress going from the bottom of the base plate all the way up through the top of the part. So one important thing to note here is that this is our yield stress, and that's through that assumption that we applied at the very beginning that the uniform shrinkage is going to cause yield stress in the top layer of the part. So then this is our relaxation mechanism that we just showed the equation for. So we're going to have our uniform shrinkage and then our bending. And then this is going to be the resulting stress after we actually cut it off, the part off of the base plate itself. Now this looks like a pretty much horizontal line. I tried to highlight that little tiny dip right there. But blowing that up, this is what that's going to look like. You can see that we get a really big decrease in overall residual stress from the part being on the base plate itself. And we get two distinct zones at either end of the part of tensile stress, and in the middle we have a broader compressive stress zone. And also that the endpoints aren't actually at the exact same stress level. The maximum stress comes at the section of the part that's towards the base plate itself. So then taking a look at tuning some of these parameters and how it's going to affect our results, this is taking a look at the number of layers that you're building up, so from 50 to 300 layers. You can see that we get an increase in base plate stress. However, our maximum stress, because of that assumption, is going in the part is going to remain the same. But we do get a decrease in the residual stress that's at the base of the part, and that's due to that second mechanism that we talked about, where laying a molten layer on it is going to cause compressive stress in the bottom layers of the part. So then taking a look at these residual stress after we remove these parts, you can see we get a really big decrease in the maximum stress of the part as we decrease the amount of layers that we're actually printing. However, we still see those same trends where we have tensile portions, compressive portions, and our maximum being towards the base of the part itself. So then this was something that I found very surprising. Varying the base plate thickness has a really big effect on the residual stress of the part itself. So by increasing your build plate thickness, you're actually able to really decrease those residual stresses that are going to be built up in the base plate itself. And eventually, when you remove that part, you're going to get a really big reduction in residual stress of the removed part if you make the base plate just thicker and more stiff. So that is a tunable parameter for someone designing an AM system to make a thick enough base plate to really reduce these residual stresses for these parts that are supposed to be immediately implemented after they're printed. So then lastly, this is just taking a look at if we vary some of the material properties that we're actually printing with. So this is varying the yield stress, or the yield stress of the material, and how it's going to affect your build. So you can see we get an increase in both the tensile, compressive, and the tensile stresses in the part, as well as the base plate. And we can also see that those trends hold for the stresses that are going to be in the part after removal. So that was all the theoretical section of the paper. Then they took what they learned from that and they wanted to compare it to actual 3D printed parts. So the way they did that is using something known as the crack compliance method. I'm not going to go into, just for brevity, I'm not going to go into the mathematics behind it. I can if anybody's interested. But the main overall idea of this method was by attaching a strain gauge to a sample, you're able to cut the sample that has a pre-stress in it using a wire EDM process at very specific depths. And then by measuring the strain, you're able to backtrack and get your residual stresses that are built up throughout that part. So their experiment was still with 316L stainless steel, so that way they could compare it to their theoretical results. And they were printing using a rectangular shaped component. So the length was 50 millimeters and the width was 10 millimeters. And that's going to be important for their scanning strategy, which can be shown here. So they tried 4 different scanning strategies. Short track method, which was scanning along the width of the part, so towards the short side or along the short side. The long track, which was scanning along the long side of the part. And then these different sector scanning methods, which they called the island methods, where they had a 10 by 10 millimeter sector and a 5 by 5 millimeter sector. So these are their experimental results that they got here. So just trying to highlight the major trends and compare those to the theoretical with this dark red line. We can see that we have roughly the same trends where we have a broad compressive zone in the middle of the part, and then on the ends we have two zones of high tensile stress. And then taking a look at the different scanning strategies, if we arrange them in increasing residual stress that remains in the part, we first have our short track method, and then there was no real difference in between the different sector scanning strategies. And then our long track method ended up having the least amount of residual stress built up in the part. So another interesting thing they took a look at briefly was post-scanning processing. So the idea was if you scan a layer, can you rescan it with the laser in order to somewhat anneal the part or reduce those built-up residual stresses? So they actually found that with no post-scanning and with 100% laser power, you don't get any reduction at all. And they justified this result by saying with 100% laser power, you're just remelting the material and you're still getting the same buildup and the same thermal shrinkage, which is going to apply the same residual stress. However, with 50% laser power, they did see a reduction in that maximum residual stress that was in the part itself. So this paper was from 2006, so there may be more research that has gone into these kinds of in-process annealing with the part itself. This is where they kind of ended it, saying more research needs to be done to understand the optimization methods for being able to do this with actual commercial methods. So then the last main takeaway here that I had was this graph. So some of the issues, if I go back, you see that you have really large error bars, or it may be hard to see in this particular figure, but you have large error bars right around the surface of your part, and that's due to the crack compliance method inherently. It's really, for a variety of reasons experimentally, it's very difficult to get your surface residual stress using that methodology. So instead you can use X-ray diffraction, which is able to very accurately get your surface residual stresses, but can't penetrate deep into the part. So to show the influence of that maximum tensile stress, which is going to be right at the surface with different part heights, they ended up moving to X-ray diffraction. And the main takeaway here is that as you build up the part, so going from 2.5 millimeters to 10 millimeters of part height, you get a really, really big increase in your residual stress buildup. In fact, we're beginning to push the yield stress of the material itself. So we're going to get yielding just through the printing process from our intended net shape that we can't anneal out. So that's the main takeaways that I had from the paper. I'd like to open it up now to any questions that anyone might have.
Questions for Ryan? Did they talk about how they measure those stresses from XR8? Because isn't it like a crystallographic methodology? Like how does that translate? That's my question.
Yeah, they go into it a little bit. I am pretty unfamiliar with the process itself, but they do go into how they use that. Let me see if I have that graph. I do not. So they go into a little bit about how they're justifying the fact that they can use this methodology and compare it directly to their crack compliance method in the paper itself. One of the interesting things that they did go into was that they took a look at a part that had no stress, so it was an annealed solid block. Using this methodology, they proved that it had very, very low stresses at the surface, so close to zero within their error bars. Then they actually took it through a wired EDM process, and they saw a really big increase in that surface stress. And so they had to actually go through and use a chemical etching process to remove that wired EDM layer in order to get the actual residual stress that they were looking for without applying a residual stress using a wired EDM.
So I have a comment. So you kind of asked about the mechanisms of XRP. Right. And my understanding is that the way in which you measure residual stress apart for XRD is the same way as you do neutron diffraction, using crystallographic methods. And what you're doing, as Ryan mentioned, they're using a reference of that part. So they're finding the exact same material by knowing basically the material properties and how much the crystal size has deformed, you can then back out what the residual stress is. You can use that to say essentially an expansion or contraction of the crystals.
It makes sense because like this purely a surface scan, so you'll only be getting the differences in the surface and not the part. So
Yeah,
right,
so
because you won't penetrate that.
the advantage of neutron diffraction is you can actually focus the neutron beam multiple millimeters into the sample.
One of the limitations for this experiment was also that just due to their experimental setup constraints, they actually had to print, and they talked about this in the paper, they had to print different parts for their X-ray diffraction and for their crack compliance method. So that was one limitation for this particular study, that they weren't necessarily testing the exact same setup of parts. And so this is good for comparing those two for basic trends, but comparing them, apples to apples, may be a little difficult. Yeah.
So you mentioned that this analysis was run for 316 stainless,
Mhm.
but then they also kind of really discussed what would change
Yeah.
results for materials. Is there anything interesting or notable from the material?
So that was taking a look at that, theoretically, that yield stress.
Okay.
Let me go back here. Yeah, so the main thing is that as you increase the yield stress of the material, you're going to begin to build up more and more residual stresses of your parts. And that's both in, your process to print it, as well as your part once you remove it from the build plate based on their theoretical model. So I think that is interesting in respect to being able to vary the build plate thickness. You have based on what you want to be printing in. To me, it was surprising you have so many different parameters that you could be varying when you design your AM process to be able to kind of counteract some of these negative effects and be able to begin to reduce that residual stress. And so it's not just that you print it and, anneal it and you have a part. There are specific things you can tune in your process itself, anything from scanning strategy to, that build plate thickness, to be able to actually begin to mitigate some of these effects.
I mean, they were showing reduced or increased residual stress with an increase in build plate.
So let's see, increase in build plate height. Yeah, so if you increase your build plate thickness, you're going to be getting a reduced stress. So if you make your build plate stiffer, you're going to begin to reduce that residual stress.
This plot is interesting, but no one would ever print on a build plate that's only 5 millimeters thick.
Right, yeah.
Because it would snap.
Mhm.
So interesting theoretical study, but they wouldn't even be able to run that experiment at 5
Right.
millimeters.
And they, in fact, they didn't do any experimental results for this because that would require you to modify your AM machine.
If I were to give a rule of thumb of what's done in practice is they make the build plate as thick as they can while still be able to pull it out with human strength.
Mhm.
They having to get cranes in there.
Yeah.
You talked a lot about
Yeah.
this yield stress, and then can you? This is probably the first thing I'll get into. Will be the first thing I get into when I start the lecture. Is this aspect, but why are they assuming that the maximum stress in the part? That was one of the fundamental assumptions. The maximum stress in the part while building is the yield stress. Why was that assumption made?
So they talked a little bit about that assumption in particular. One of the issues they brought up that if they didn't cap that, I believe if I understood the paper correctly, if they didn't cap that, you would get really, really high stresses in that material part. So you'd get really high peaks. And so I believe just to make the model work, they did that, but there may be a better, more scientific solution. That was one of the things they mentioned.
Okay, so the reason why there's two aspects. One, they cap it, right?
Mhm.
So that makes, from a solid mechanics point of view, that makes a lot of sense because if you look at your stress strain curves, right, you hit your yield stress and then you have a lot of essentially strain for not much increase in stress. Okay? And so that makes sense that once you hit the yield stress, that's really, once you go past that, then it's just the part is yielding and the stress is no longer building anymore, right? It's just dropping back down to that yield stress. So that makes sense. I guess maybe I'll rephrase the question. Why did they forced that at the height of the part, they forced it to be the yield stress, where you could potentially have a stress that's lower than that, right? Did they give any justification for that?
They might have, I didn't pick up on it when I read through the paper myself.
I'll talk about it a little bit in a few minutes. But basically, you always get your stress in your part reaching yield stress. And we'll go for a really simple example with just a few hundred degrees Celsius increase in temperature, you hit the yield stress of a material pretty quickly. So that's a fairly good assumption that you're going to hit the yield stress of the part, always. So you're going to have material yielding as you're building the part. Other question I had, it wasn't clear to me why they made the base plate have 2 times the modulus of the material you're building with. That's a big jump.
Right.
If you look at like the variations in metals, especially if you're saying I'm going to print 316L on top of a 316L plate, I don't know how they would ever get a 2x difference in the modulus. Did they
Right.
justify that at all?
It didn't appear that they just kind of assigned material properties for their theoretical model. One of the interesting things they talked about that I didn't go into here is that they also talked a little bit about we're only looking at a 2D cross-section. However, the width of the base plate isn't necessarily the same as the width of your part. In most aspects, it's not. And that is going to have an effect on the effective stiffness of your part itself. And so they talked a little bit about how you could add widths of the base plate and the part to your ratio.
So they're essentially fudging it by
Yeah, this ratio.
changing the modulus.
Yeah, yeah. So that might have something to do with it.
Any other questions? Okay. All right, thanks, Ryan.
Dr. Moses, this might be a question more for you, but you mentioned that they often make their build plate as thick as possible, and still be able to remove with human strength.
Yeah.
Is there an upper limit to how thick that you would ever want to make that, so that, you stop getting benefit? Like, I mean, 10 feet by 10 feet, would it just be,
Yeah, I'm sure there's going to be some sort of
some kind of,
diminishing returns, yeah. But yeah, they're usually somewhere on the order of 2 inches thick. So let's say you're building something that's, the actual build size of a lot of machines is very large, so around a foot by a foot.
right?
But a piece of stainless steel that's a foot by 2 inches thick is really heavy. Like that's gonna, I'm not saying that you couldn't lift it, people definitely can, but it's not something you want to do all the time. It's like, I was a little bit joking, but I mean also there's cost associated with it too, right? That's much design where you have to spec out the cost of metals to build stuff, and build plate costs a few $100s just by my estimation. Okay, so we're going to talk about residual stress and deformation, which we had a pretty good intro to this right now. So to get into this, we're actually going to start off with a really simple example to kind of eliminate some of the aspects that we just talked about here. So this is an example where we have a material, and this material has these dimensions you'll see in a second. L and then the cross section aren't going to matter actually. But we'll show why those drop out in a second. But
the example here is we have 316L stainless steel. We were saying nothing about how this was made. Choose your favorite manufacturing process. But it's held between two unmovable constraints at room temperature with no pre-stress in it to begin with. And then you're going to say that the temperature of the bar by some sort of heating mechanism is uniformly increased to TF. All right. We're going to assume that this happens slowly. There's no shock in the material. So determine the average normal thermal stress in the bar as a function of TF. Okay. So some things that we're going to assume here. Assumptions. So we're looking at the average stress. That was given in the problem statement, but just make sure that's clear. The average stress, we're not talking about what happens at maybe possible stress concentrators in this. So average stress sigma. And that this stress never exceeds yield stress. So we're going to raise the temperature to TF, and we're going to keep on raising temperature to TF until we hit the yield stress. And we're going to see where that happens, actually, in terms of what temperature. Just trying to understand that. If once we hit the yield stress, then we have to look at out-of-plane deformations, things of that nature, which is going to get a little bit messier with the equations here. So I think everyone probably is very aware of this, that if you heat something, in general, it expands, right? So that is what we call the coefficient of thermal expansion. So this is just some examples of what I mean by the coefficient of thermal expansion. This is essentially directly what we're talking about here. The variables that this source uses a little bit different than variables we'll use, but basically you heat up this bar, and you get the change in length divided by the normal length is equal to alpha, and alpha is our coefficient of expansion, times the change in temperature. So it's just a material property that explains how much a piece of material expands as we change temperature in that material. Right? And I think everyone who's probably saw this in, say, freshman year or even high school physics, probably. Probably high school physics, right? And so then we can look at this for different materials. And so for metals, there's not all that much variance in metals. These are all somewhere in the same range. Here are just some common materials that we would potentially use with additive manufacturing. This case, we're using stainless steel, so this can be an order of 16 times 10 to the negative 6. Units are here meters per meter, so that's just basically representing the change in length over this length times inverse Kelvin, right, in terms of how this scales. And so this phenomena explains why when you drive over a bridge, that's why engineers put little gaps at the edge of a bridge, right, so your bridge doesn't buckle. Explains why if you don't do this correctly, you get railroads that look like this. Kind of some typical bloopers of engineering right here, right? So this explains why these types of behaviors happen, and then it explains a lot, pretty much everything in terms of why parts distort while we print them in additive manufacturing. Okay, so going back to our question, we say, okay, try and compute this, or we're going to compute the stress as a function of temperature here. So what we get is we get this scenario. So let's assume that we removed that top wall. All right, so we have this constrained, or I guess we'll call it the ceiling. Say we remove the ceiling of this part, right? And so then we have this scenario. So we have our bar, we heat it up, and then we're going to get some sort of thermal distortion we'll call delta T. So delta T would be equal, given our equations that we have, alpha delta temperature times L. Okay, but we do have a wall or a ceiling at the top, right? So then we can look at, all right, what would be the force required to take this bar and actually move it back down to this position. So this is going to be a delta force. That's basically we're balancing these strains, or these, not strains, but deflections. So we have then delta F, and these are established relationships, that delta F is equal to force times length over area times the Young's modulus. Now keep in mind, with just typical normal compressive stress, force over area is stress, right? Okay. So if we want this system to be basically in equilibrium here, we have to have a delta T minus delta F is equal to 0. And so that just then creates, basically putting these equal to each other, we get then alpha delta T L minus sigma L over E is equal to 0. L's cancel out. And so then I get sigma is going to be equal to alpha delta T times the Young's modulus for this material. Okay. Any questions on this simple example? Okay. So for 316L stainless steel, alpha is equal to 16 times 10 to the negative 6. Young's modulus, 165 gigapascals. That's 10 to the 9 pascals. This is from the source on the previous page. And this is actually in that survey article, the Debroy 2018. All right, so then we can now find a relationship for stress as a function of a change in temperature. Oops, forgot delta P, delta T. Keep in mind, this is from the Debroy paper as well, that the yield stress for 316L stainless steel is going to be equal to 435 times 10 to the 6 pascals. Okay, so I can look at these here, all right, and say, what can the temperature difference be before I start to yield this material, right? And so you can look at this and say, all right, these are both 10 to the 6. Somewhere around or a little less than 200 degrees centigrade or Kelvin, which is not, compared to the type of temperatures that we're using with additive manufacturing processes, that's really not that high, right? That's a pretty small temperature. So we can plot this. So here would be showing a linear change in the stress. We said that this is the range we care about. We said, all right, we're saying this model is approximately valid for temperatures such that the stress is below the yield stress. Above this, other things that are more complicated are going to happen. But we can see somewhere in the order of 170, maybe a little over 160 degrees centigrade or Kelvin, we get material that goes above the yield stress. Okay, so that's the main point of this little exercise here, is to show that it really doesn't take all that much temperature gradient to get a material to yield with these types of processes. In this example, it's independent of length, but that's the main point here. So it's pretty safe to assume, and there's a lot of evidence showing this, that we're always going to get material yielding when we start talking about additive manufacturing of these types of materials here. So that's the main point of this simple example. Any questions on this simple example? Okay, so of course then our parts don't look like beams like this. They're a little bit more complicated than that. So I thought it may be helpful to go through a case example of, this is a fairly similar paper to the one that that Ryan just presented. This is work that I was a part of. I used to be a professor at Notre Dame. This is a 2-year project that we worked on, looking at residual stress in parts and also deformation in parts, printed by laser powder bed fusion. So using an EOS system, we looked at this for 316L stainless steel and also aluminum printing. I thought it'd be good to go through some of the results of this before we get into some of the physics. I thought it'd be interesting for everyone to look at. Okay. So this is I would call this a case study, and we were looking at paper Ryan just presented were essentially rectangles. We were using an even simpler shape than that. So rectangle is a 2-dimensional material. We're using a disc. And so the reason why we wanted to use a disc is we can actually quantify deformation by a single parameter, which is essentially the radius of curvature of this disc as we print. Okay, so what happens when we say we want to print this disc? Whoops, I didn't intend to write. We want to print this disc. This is ideally what we want to print. And we print it, and what ends up happening is when it's on the build plate, you have a ton of residual stress built up into this material, and then when you release it from the build plate, it folds up into like a bowl, or what we call it, a potato chip, essentially. So now when I say this folds up, we're talking about if you were to have it on your desk, you may slightly be able to see that it's folded up into a potato chip type shape, but with a coordinate measurement machine or something more sophisticated that we would use in an engineering environment, you can definitely measure this potato chip effect and this bowling up of the part. So we're using this as a very simple artifact that we can then try and extend to something more complex. This is actual parts that Johnson & Johnson would print. These are essentially handles that they'd have for their different manufacturing operations. And here's a direct result of too much residual stress in the part. So this doesn't show everything, but there is basically something over here. And basically the worst thing you can do with additive manufacturing, which is very much a big problem that they're trying to solve, is trying to make long, slender parts. It's pretty good at making things that are somewhat the same dimension in all directions. Right? So if you try to make long, slender parts, you get a lot of residual stresses in this direction, which then cause the bending or pulling up of this part, and then this is breaking away from the build plate. So what the engineers at Johnson & Johnson did is they used the normal support structure, which we went through in, I think it was module 5 here, but then they also recognized that they're going to get a ton of residual stress in the part, and so they made these pyramids here that are solid metal. So actually part of the material to hold this down while it's printed, and even then it pulled away. So it basically broke what's somewhere around a 0.5 centimeter structure just away from the part, even though they try to reinforce it anymore. So this is basically the worst thing you can try and do, and so this is a very real problem with additive manufacturing. It's definitely not solved yet in terms of how do you either print something like this or design better strategies in terms of how you lay this on the build plate such that it's going to print properly. Okay, so that's what we were looking at this very simple example for. Oh, I forgot to mention, this is funded by America Makes. How many of you, I think I mentioned America Makes, but how many of you remember that or have heard of America Makes? Okay, so America Makes is the very first of the advanced centers of manufacturing in the United States. These are kind of an attempt to model after the Fraunhofer Institutes that are in Germany. There are these manufacturing research centers, and this is in Youngstown, Ohio, actually. This is their very first one, and it was focused purely on additive manufacturing technologies. And so they funded, they're still funding projects, but they have a bunch of machines there, so if companies want to go and try out a process, they can go use their machines. Of course, not for free, but for a certain cost, but actually a pretty reduced cost. And then they also funded a lot of research projects, and that's what we were funded under to look at this. All right. So this is the main problem. We're going to be printing disk. That's basically what we're doing here. So this is basically what Ryan was talking about before. We were looking at trying to understand this as opposed to they were looking at more continuum mechanics in that paper Ryan just presented. We were using finite elements to try and understand this. But the main idea here is exactly as Ryan said. You have, I think one detail that the paper didn't go into is what is the state of stress in the melt pool. And it's pretty safe to assume that the state of stress in the melt pool, relative to the state of stress in the solid material, is 0. And you can think of this if you were to take like your finger and put it through the melt pool. I wouldn't recommend it, but it would essentially have no stress built up into it in terms of the resistance you get if you try to put your finger through a piece of metal, right? So very, very different. So we have essentially 0 stress in the melt pool, and then as soon as it starts to freeze, then you have stress accumulation. So what you're getting is you heat up this build plate. You're creating a melt pool directly under the melt pool. You are getting very intense temperatures that are just below the melting temperature of that part, or that material. That's causing thermal expansion. Then this material on top freezes, and then when it freezes, it's essentially at the melting temperature, and then everything is then cooling down, and then you get thermal contraction. This is what you get in this area. And so then, as it's held on the build plate, it has residual stress in it, and then when you cut it off, this is showing the act of cutting it off from the build plate, then it kind of rolls up like a potato chip. Okay. And so then this is a very, I would say, sequential operation here, where this would be, if I wanted to look at what is the temperature at any point in the part, I have melting and then I have cooling happening continuously. So if I look at T1 here, corresponds to the first layer of material being deposited. I have heating up to the melting point, or the solidiferous temperature. It then cools down. And then my next layer comes on top of it, and because the layer above it is hot, it's heating up my first layer. So my first layer is cycling through all these different temperature profiles. Okay. The act of freezing in the material locks the material into some sort of configuration. And so if I wanted to understand what is the accumulation of stress in the part, I can look at these individual time indices in which the material locks into place at the top layer, and I can just start to stack up all these individual layers that are being held into these different configurations in terms of looking at the thermal expansion and contraction is the main idea here. Same thing happens with layer 2. It heats up to the melting point, goes down, and then it goes into this profile, and the next layer goes down. I will do a note, when we talked about layers here, we were looking at very computationally efficient means of computing this, and so our layers were it was a pseudo layer. It was much larger than the layer that you get at the actual layer in terms of each recoding operation. So this is on the order of around 1 millimeter, where usually the layer is on the order of, say, 50 microns. Yes?
So looking at this graph, we see that once we apply layer 2 and layer 2 begins to be reheated by layer 3 being applied, its peak point of temperature is above that the reheating of layer 1 compared to layer 2.
Yes.
Is that due to like a buildup of heat as we talked about with each layers?
Exactly. So what's below it, you can think of it almost as like a new boundary condition, right? Okay. And that's at a hotter temperature than the substrate temperature. So that's the basic idea of what's going on here from like kind of a 1,000-foot view of what's going on. We did finite element methods. This is just showing kind of the artifacts we looked at. We looked at these parts, which we could break down into, we were using cuboidal elements for some very practical reasons in terms of, I'll go into the real details of that, but this is pretty efficient in terms of making sure your top surface is smooth, and you can also build up multiple layers as opposed to the more complex finite element meshes you get would have jagged interfaces at these layers as you go up. But then we're looking at parts or disk that were both printed normal to the build plate. So sorry, this doesn't have axes on it, but this would be the Z direction. And then we were looking at ones that were angled from that as well, trying to understand how does angling the part affect the distortion of this part. Ryan, you're looking very intently here.
Yeah, I'm trying to see your voxels in figure B there.
Yes.
Are they angled in such a way that that remains a smooth surface?
It is not.
Okay.
Yeah.
I couldn't tell.
Yeah, it's a little small, yeah, but they were not there. Okay. So this is for our models, And then here's the experiment that was done here. So this is fairly extensive experiment. This took a lot of time, I would say. I guess looking forward to your projects too. Remember, I said that assume that you have essentially infinite resources, right? Not infinite. You can't say I'm going to do design of experiments of the entire possible set of additive manufacturing treatments, but assume that you have a lot of money to play with, that you can hire technicians, et cetera, to run a lot of parts. So we looked at, I don't know what the number is, number of samples we actually printed. It's quite a few. So, close to 100 parts that we printed here for this study. And so then each of these were also characterized, which takes a lot of time. So this was essentially a graduate student and a postdoc, about a year and a half of their life was making samples and characterizing them, somewhere in that range. They were doing other things too, but yes, Prasad.
Why such a huge variation? Like, is there a reason why you're focusing on?
Yeah, so our primary sample that we were looking at was this 45 millimeter diameter, 5 millimeter thickness sample, because via pilot studies, we would get, that's somewhat in the deformation range that we were looking for in terms of trying to characterize. It was where we could start to pick it up in the CMM, but we weren't getting so far out of some basic beam bending and linear analyses we get. We didn't want something that would pull up like this. Yeah. So we printed a lot of these. The other thing that we did that I'm not going to talk about in this presentation is that we mostly printed them in this configuration where we would put, this is 15 on a single build plate, but we were also interested in whether or not there's variation in if we just print one of them in the center in terms of deformation. And so actually a lot of these were a big waste of money in that we would print just a single one of these in the middle, and that was it. And to try to understand, is there a difference actually in deformation and stress? And in terms of deformation and stress, we found that there was not. Yes?
Yeah, that was similar to the writing milling, but they found that base plate heating wasn't really
Okay. Yeah, so a lot of these were just making sure, like a kind of somewhat of a pilot study, making sure that we're not artificially inducing an artifact where if we print in this region here, it behaves differently than if we print in this region. So the answer is essentially no. And then we also looked at, if we look at what we did here, we had a lot with angle of 0, so that's what you're seeing right here. We had a few that were printed at an angle, just to understand what happens when you print at an angle. And then we looked at changing the diameter. So that's this plot here, this is 45, and then we're going up from 45 here. And then also we looked at changing the thickness. This image is not so good in terms of trying to understand what the thickness is, but we're going from a thickness of 1 millimeter all the way up to 30 millimeters, so having very, very thick parts. And so this is getting to where you're getting a thickness that's getting to be on the order of the diameter of the part. It's getting to be more regular in terms of same dimension in each direction. And then what we did in terms of characterizing this is we have two main ways in which we characterize this. One is a coordinate measurement machine. Has anyone used a coordinate measurement machine before? Nate, you have? Okay. So a coordinate measurement machine, you can see the stylus of it here, touching the part, but basically you have this XYZ gantry system that's above the plate, which we have here, and then it's basically a robot, and this robot will go along and it'll scan the surface of this part. It has a little touch probe, so it knows when it hits the part, and then you get the topography of the part via this measurement machine. Right. It's pretty automated, so you just kind of let it go. Right. So it's a pretty quick way to try and understand what is the surface topography, and then from there we could characterize and take that set of data that comes from this. There we go. Sorry, I didn't realize that was an animation. Here's the type of data you would get off of it. This is just a heat map. The blues are lower, the oranges and yellows are higher, so you can see that it's bowling up like we said it was going to. And then from there you can fit all this data to what we call a radius of curvature, so this gives us a single number of what is a metric of distortion. So basically ROC goes up, ROC goes up. Sorry, I'll write this more neatly. Distortion goes down. And then vice versa, right? So if we have a very small ROC, that means this fits a very small sphere, so therefore it has a lot of distortion in the part. All right, the other thing that we did is we took these samples, and the postdoc ran up to Canada, like the middle of nowhere Canada, where they have this neutron diffraction machine instrument, and he was characterizing the stress at different locations in this part. So this is trying to get similar data that Brian presented, the crack compliance method, which has some problems with it. One of the problems that he didn't mention is that it's destructive. Right? So this is a non-destructive way to try and get the stress in the part. And so this is nice in that way. The main negative is that you have to send a student to Canada or Oak Ridge or Argonne. There are not too many of these things. They're not just like lying around.
You might find someone willing now to go to Canada.
Yeah, okay. Do you want to smoke pot or what? Or are there political reasons? Yeah. Student may never return, I don't know. Anyhow, so this was measurement. We were taking measurements of the residual stress in the part, both on the build plate and actually after it's been released at these locations. So this is different locations on the top surface and also different locations within the depth of the part here. All right, so we did both simulations and experimental results, so I'm just going to run through some of these here. Help orient you what's going on here. This is a heat map. On the top here is a heat map of distortion, and then a heat map of then the stress in the part. Right. This is a von Mises stress. This is essentially principal stresses in the part, not giving a direction to it. Okay. So this is also this is aluminum. I'll go through the case of stainless steel in a second. Nothing too fundamentally different with this, but the main message here is that when it's on the substrate, you get a very little, almost imperceptible deformation because it's being rigidly fixed to the substrate. And then when we release it, you get a pretty large deformation, essentially the effect of it popping off, right? And now it blows up. So when it's on the substrate, pretty flat, very minimal distortion, you have the ability to relieve this residual stress via post-process heat treatments, which we'll talk about later in this module. But that is an extra expense in your manufacturing process. And, so you may not want to do that, but you will get, if you remove this, you get this pretty large distortion. So you get somewhere on the order of 0.3 millimeters. If you look at the very bottom of this is around 0, all the way up to 0.3 millimeters distortion you get in the part once you relieve it. The stress is the opposite case. So when it's in the when it's on the substrate, it's in essentially the highest stressed configuration, and then you take it off the part, and then the stress relieves considerably. This is very similar to what Ryan was showing as well, right? Where you showed the residual stress after you relieve it, it goes down considerably. You see now we're much more into the blues now, as opposed to being way into the reds with this type of material. The experiment compared to simulations. So this is our simulation. Of course, if it's a simulation, it's going to be exactly the same ROC every single time. So this is not, actually, I think I accidentally covered up the x-axis. This is sample number. All right. Okay, so if you do this every single time in the simulation, it gives you exactly the same answer. This is then the actual residual stress that we get, or sorry, the radius of curvature that we got from these parts. This constitutes about a 16.5% relative error, which is fairly reasonable for how simple our models were. But we're getting in terms of the ballpark in terms of understanding what this distortion is. This is with 316L, so it's exactly the same plot, just a different material. Our relative error was considerably lower in this material for reasons we don't exactly know why, but basically we were on the order of the error we're on the order of, basically our simulations were fairly accurate in terms of understanding what the radius of curvature would be. This is looking at deformation of the angled parts. This is the 45-degree angle part. And this is showing the patterns if you scan it with the CMM versus what we predicted, which had some similar features. So not a perfect 100% match, but qualitatively fairly reasonable approximation of the type of behavior we would expect here. Any questions about this thus far? Okay. Looking at this radius of curvature as we vary other parameters. So these were just like a bulk. This was basically testing a bunch of the same thing over and over again to try to understand what's the variability in this process. Seeing that there's fairly little variability. And then this is looking at single prints at now varying different factors here. So this is as we vary the diameter. So we hold constant the 5 millimeter height of that disc, and now we vary the diameter. So this is what we tested a bunch of right here. And then this is then our different treatments for aluminum, showing pretty good correspondence here. And then this is varying the thickness. So when you start to get very, very thin samples, these are, you have to take in mind what the aspect ratio here is. This is a 1 millimeter thick disc that's 45 millimeters in diameter. It's like, I don't know what the base compare it to. It's basically a really wide washer. And we would see in the CMM that we're starting to get buckling in these types of parts. This is getting some sort of asymmetry in the deformation behavior, which wasn't explained by our model. So this is a region in which our model doesn't seem to work so well. But this is getting, the radius of curvature is really, really small here. So this is a pretty extreme deformation that we're getting when we make very, very thin parts that have a really wide diameter to them. So like I said before, the worst thing you can do with additive manufacturing systems right now is you make something that's really long in one direction and very short in the other direction. And that's exactly what we're doing here. We're making a very short part that's very long. In comparison, it's creating a lot of deformation in terms of the radius of curvature going way down here. And then as we go up in thickness, the radius of curvature goes down. And then out here, off the chart, we decided not to report these values at, I think it was 20 and 30 millimeters, because our deformation was so low that we couldn't actually get a sphere to fit to it. So it was essentially a flat structure. So the radius of curvature measurement was really kind of fictitious in that extreme. And it wasn't bowling up at all, because it has essentially, even though, as Brian showed and what we showed, is that you have a really large residual stress in it, but it has now a really large moment of inertia associated with that, so it's actually not going to distort much. Okay. Residual stress measurements. This is where maybe our experiments in our model was, I would say, qualitatively the same, but had a decent amount of quantitative difference. This is simulation, so the open symbols are simulation, then the filled ones are actual measurements that we took off this neutron diffraction machine. So main message here is that you get stress profiles that somewhat qualitatively match what you would expect here. So the blues essentially match the blues, the reds somewhat match the reds, and then the pinks somewhat match the pinks here. The other thing is that the stress in the Z component is really, really small. So this would be stress in terms of the stress of individual voxels being stressed along the length of where you're printing, small. In the X and Y direction, quite large here. Okay. All right. And then also we did some things that, this is going back to module 8, just to kind of tie this all together. These are looking at grain structures in the parts. So this is the Z direction. So this just shows you individual grains. Z direction, this is our build direction. This is then the top down. This is looking at the top down. So we said before that the main structure you're going to get in here are these columnar grains, kind of stacked like this. And that's essentially what we're getting. So this is probably one of the least interesting results we got in the study, because this is basically matching what everyone else reports on, which just demonstrates that this is in compliance with everyone else's results. So this is showing primarily these long, elongated grain structures in this direction. If you look from the top down, and you see then the top of these grains. You can also start to pick out where the melt pools are and correspond. You can actually match this to images of where these melt pools are. These are the overlapping melt pools that you see in here. Again, showing that some of the grains even pass melt pools in this. And then this is the same exact experiment, but for characterization run with the stainless steel part, showing very similar behavior as well. Okay. All right. So then this is, I guess, I would say more of a scientific study. And then the question is, where can this potentially be used? And so how we've used this information, I kind of glossed over it at the beginning, but if you look at our models for residual stress buildup, this temperature profile, we were investigating very, very efficient ways to try and get this temperature profile. And then we were also looking at quasi-static analysis, assuming that this material is freezing into place at only distinct periods in time. And that's a much more computationally tractable way of trying to understand and characterize these deformations than if you do a full spatial temporal finite element mesh. So the full spatial temporal finite element meshes, if you want to do this for the part, it's going to take you multiple days. We were able to, by making some simplifying assumptions, get answers on the order of just a few minutes, actually, in terms of what these, what the distortion and stress in the part would be. So what this enables us to do, if you have a model and you can have somewhat reasonable validation of that model with experiments, you can start to look at, all right, how can I use this for design? And I mentioned that the worst thing that you could do is basically create a part, and then this is the build plate, and you have something that's long and slender, and you lay it flat in terms of distortion of this part. And so, okay, if that's the worst thing you can do, what's better, right? What are your options in terms of how you orient this part? And so you can, essentially, you can rotate this part along 3 axes, right? You can rotate it in alpha, beta, gamma, right, in terms of your angles of rotation. And so then the question is, what would be the optimal orientation for a random part? And what you can do is you can start to build then, if you have a prediction of what the temperature history and distortion is, you can start to say, all right, I want to make this my objective, and I want to try and minimize the distortion of this part, and then continually change orientations and try to understand which one is the optimal orientation to build this part, is the main idea here. And so how this is done primarily is you have technicians who get really, really good at how to orient a part, so they know it's going to print properly. But that knowledge, or getting really, really good at that, takes quite a few months for a technician to get good at it, and that's not really too transferable. So we're trying to make software or computer-aided manufacturing tools to try and automatically choose orientations for parts that you're going to get low distortion coming off the machine. So what that means is you're using these loops where you at first randomly choose an orientation, you generate support structure from that, and then you compute what primarily we're mentioning, what is the distortion, right? And so then you can then say, all right, now given this distortion, I can change the orientation. And we were using a somewhat random way of going around the entire 3-dimensional angle space to do this, and to then continually go around this loop until we converge to some sort of orientation that is optimal with respect to an objective function that weights distortion. And so this would take somewhere on the order of 100 iterations to do, going through all the possible angles. And so what that meant is that we have to do this step really, really fast. We can't take on the order of a few days to do this. We have to do this in a few minutes, right? If we want to get an answer in about a day, is what we were really shooting for. So we were shooting for this computational method to happen in the order of tens of minutes. Okay, so how can we use this? So here's an example of a part that, and this is, I passed around this part earlier in the class. This is not actually, what you're seeing here is not the part that was passed around. This was, actually, this one is the one that printed without defects at all. There was actually a small little defect on the base of the one that I handed around. But what we found here is that this was what the algorithm determines to be optimal. And what it's doing is it's taking a pretty long, slender part, which is, and I'll show examples of cases where this fails in the next slide. And what it's doing is it's creating or reducing the cross-sectional area of any given layer. So we know that the residual stress is going to cause, when it cools, thermal contraction at that top layer, and that amount or total deformation is going to be proportional to that cross-sectional area. And so what this is doing is actually finding an orientation in which it's has minimal cross-sectional area. It's also finding one in which is minimally constrained. So we have to support the part somewhere. If you go down just a little bit lower to get efficient thermal transport, you have to support it the whole length, and then that creates a thermal constraint and it's holding it fixed. So actually it's better to have most of the part entirely free, as long as you don't hit some sort of temperature limits. So in this optimization, we actually had bounds on what the temperature could be, because if you want to get minimal stress, you actually print this completely vertical. And so that is another constraint that we tried to hold down, but that part would get really, really hot. So this is what is determined to be optimal. This is the path it takes to find the optimal temperature. So what this is showing here, all the blue lines are this objective function, which, without going into the details, the objective function is primarily what is the distortion of the part. It's basically a metric of distortion with some other things thrown in there in terms of weights or penalties for having a temperature that's too high. And you see that most of the orientations it randomly, it's not completely random, it starts to narrow down on a better and better answers. Most of the orientations it chooses has a really poor performance, but every so often it finds a really good orientation. And that's these blue ones. Every time we find a good orientation, that moves this red dot down farther until we get to one that's even better. And so then this is then this objective function eventually converging after around somewhere 100 iterations, and this took us around 22 hours to do this on actually just a desktop computer, nothing too fancy. All right. So then the question is, how does this do compared to other options? So at Johnson & Johnson, they had a bunch of interns that they could go and say, all right, you have to go and learn how to do this properly. And this is Danny the intern. And so Danny the intern, with given essentially all the resources he wanted in terms of being able to read, research, do anything, even except for talk to the technicians who are experienced with this, was able to finally get this to print. So this printed it without failure here. It took them, I believe it took them 6 times to get anything to print actually. And so when we talk about not print, we mean a recoder blade would distort so much that the recoder blade would crash into the part and abort the part. So this took 6 times to get, and what he had to do is actually, just like you saw on the earlier slide where they turned the support structure into solid part, he had to turn it into solid part at the edges to get this to print. And then when you pull this off of when you actually remove this via wire EDM, this is the distortion profile as measured by CMM at the tip. And so just to kind of show you this is off the page. This goes up to, actually distorts around 3.5 millimeters. That's pretty much not within any manufacturing spec, 3.5 millimeters. So you can imagine the amount of residual stress that's built up in here to get this pretty thick piece of stainless steel to distort all that much. And then this is then the, after we pulled off the build platform, this is the distortion in our part on the order of less, I don't know exactly what this is. It's well less than a millimeter though, in terms of distortion at these far regions here. Just by changing nothing but the orientation angle at which we print this part. Some other caveats, so this would take, our print took much longer because it's higher, right? So that means you have to pass a recoder blade over it more times. That means you're using more powder as well. So there are reasons why this may be beneficial to your manufacturing process. Because it's going to take less time to print, it's going to use up less powder, which we talked a little bit about powder reuse. Powder reuse is not, it's not a perfect recycling process. You do lose some quality in the powder with reuse. So there's all these kind of engineering, manufacturing trade-offs that you have to consider here. But if you wanted to get this to print with minimal distortion, this would be the angle which you would do it. Any questions about that study? Yes?
So, the paper that I presented talked a little bit about in-process annealing.
Yes.
Did you consider that at all, or were you focused mainly on no, post-processing of the part itself, just one print and we're good to go?
Yeah, so this was no post-process annealing. We wanted to be able to print parts without having to do the extra manufacturing step, was the idea. In-process annealing, we were not looking at relaxation of residual stress, which is more of a microstructural phenomenon, right? You actually have grain boundaries realigning for that to happen. So we did not have that in there. What I would say, though, is that what we're doing is to make this happen quickly, we're masking a lot of what's going on at the melt pool level. So going back, this is what we were calling super layers as opposed to a single layer. And so what we're doing is we're lumping a lot of things that would happen at very high residual stresses at the melt pool, and it's lumping into a larger structure. And then we're saying that larger structure is then freezing as opposed to all these little micro welds. And so that's not really a scientific answer to your question, but we're essentially muting out a lot of the effects that need to be annealed away by making larger scale structures. Okay. Any other questions? Okay. All right, well then we'll get into some notes on solid mechanics and how to predict deformations, etc. on Tuesday then. So, all right, have a nice weekend.
Okay, yeah.